Hi, everybody. It's Konstantin Läufer from Loyola University Chicago, Theory and Practice of Programming Languages, Spring 2016. And in this video, we're going to talk about the dynamic semantics and the actual resulting implementation thereof. So just to recap, in the previous video, we discussed the formalism of structural operational semantics and the use thereof to express formally the working intuition we already have of the semantics of a typical imperative language. Kind of this common imperative core among languages such as C, Python, JavaScript, etc. So just to recap, we looked at the key addition to the expression syntax, which is a variable, and the new statement constructs, which were assignment, loop, and something we didn't call block, but it's basically equivalent. We called it sequence. So statement S1 followed by statement S2. So block is just a generalization of that, as you know from the project work. And it's basically 0 or more statements. And of course, you could use the sequence construct S1 followed by S2 and continue expanding that until you have the desired number of statements. But it's often more practical just to define a rule for saying 0 or more statements, using something like the clean star. Great. Now, what's new here is a conditional construct, and I will leave it as a challenge to you to express a conditional in basically any language that has something like a while loop, using while loop. So that's always a transformation you can do. But here in the actual project, we're going to provide direct support for a conditional built into our mini language. Okay. So what we did was study these structural operational semantics, and what we're going to do now is look at the actual implementation for the simple imperative language, which is tied to the previous video and the corresponding handout. Okay, and let's take a look at that. So here's the underlying abstract syntax, very familiar. Basically, the expression language that we have here, so the applicative side effect free constructs, and then the imperative additions are, of course, this one here is on the expression side, as we just discussed, so a variable with a given name, where we use strings as variable names. And then we have the new imperative executable statements. And this one is already, in fact, defined like a block in your project. So 0 or more statements would be a sequence. Okay. And this is, of course, an instance of the composite pattern because sequence has 0 or more children of a type statement, and at the same time, it is of type statement. It is a statement, okay? Whereas these others, well, you could also consider these composite nodes of fixed numbers of children, so 2, just kind of like the plus and plus, minus, etc. Expression nodes. Okay, so while takes a guard expression and a body. And assignment has a left side and a right side. Okay, so using this syntax, using these constructs, we can represent these programs in the simple imperative language. Now, it deviates a little bit from, let me pull it up, the actual syntax we had given here. And that's actually okay. So the main deviation here is that there's a distinction between expressions and statements here, whereas that distinction goes away. So you might ask, why are we getting rid of this distinction? And the response is it's just easier from an implementation point of view to have just a single type of syntactic node, and that would be statement. And you might say, well, but then we'll lose certain checking that would happen automatically as we're constructing the abstract syntax tree. And well, we could say, okay, that's true. We're losing some of that, but as you're writing the parser, you're likely to be careful about what syntax trees you're going to build. So it's maybe of questionable extra value to have that, because the parser is something that probably doesn't evolve much, and that stabilizes quickly, and you can test it and then gain confidence in its correctness in that way. Okay, so I'm actually making an argument against static typing here in this particular case. But now coming back to what we're actually trying to do, in fact, I am really making an argument in favor of separating the syntactic concern of building the abstract syntax tree and then validating that by performing some kind of type checking as a separate optional stage that we're not really doing in the projects, but it could be addressed easily as a separate concern, just making sure that some kind of static checker that makes sure that the abstract syntax tree makes sense beyond its correctness, its basic correctness at the host language level, where I mean, in this case, Scala or whatever language you use to implement the interpreter. Okay, so that's why it's just kind of unified, and there's no distinction between statements and expressions at this level. Very good. So this is then pretty straightforward, and now what we're going to do is look at the implementation of the interpreter, which we would expect to be a very faithful, close implementation of these rules. So, of course, we have the part for evaluating expressions, which will then include, or where we will add the branch for evaluating variable, and then we will have more branches that we'll have to add for executing these imperative statements, these new constructs. So let's take a look. And we will start with a representation of these concepts that have their history in the C language or earlier. The idea is when you look at an assignment, you have the right side and the left side. So variables can appear on either side. So let's say a statement such as x becomes y. So x on the left, then the assignment operator, and then y on the right. So what is the difference between the way we're using these variable names on the left and on the right? Well, on the right, what we're doing is evaluating the variable as part of an expression which happens to be just the variable. Or it could be something like x becomes y plus 1, or it could even be the same variable, x becomes x plus 1, right? So if we evaluate the x on the right side as part of the expression x plus 1, we want to know what's currently in the variable. So it could be a value 5, okay? And that's the idea of the R value. The contents of the variable that appears on the right side of an assignment as part of the expression on the right-hand side. Okay, and an L value is when we're assigning to a variable, we don't care what's currently in the variable. That's going to get thrown away. So we're just going to invoke basically the set method on that variable as discussed in the structural operational semantics, right? So that is what we're interested in when we're using the variable on the left-hand side of an assignment. So we're interested in the variable as a container of a value that we can stick into the variable. Now, a storage cell or storage location, that's here on line 16, that is something that can be used as an R value and an L value depending on where it appears. So that one has that one is just basically an implementation of the L value trait, right? Because L value already extends R value. So we're saying R values can appear only on the right side of an assignment, and L value adds the setter so that it can appear also on the left side of an assignment. And a cell implements that, and we're doing this as a case class. And what's a little unusual, we haven't seen a lot of case classes so far where the attribute or instance variables are mutable. So that's what we have here, because we're representing, implementing the idea of a mutable storage location. Okay. And then we're creating a useful little companion object that has a predefined null instance. And that's just, it's the same. We could call it null or zero. I like to call it null because, as we will see later, there's really no distinction at the implementation level. And in the C language, it's kind of like that. There's a predefined null also. Great. So now we have the ability to represent these storage locations. And the next step is to build the interpreter on top of that. So the first thing we need is a way to represent our memory store, and that's right here. So the memory store is a map, as discussed in the conceptual handout, a map from variable names represented as strings to L values, where we will have cell instances, because that's our implementation of the L value concept. And here we're dealing just with ints. So we'll just specialize the type of the value in the L value to int. Okay. So we have a store for our named state. So in other words, these unnamed storage locations become named state because they're going to live in this map. Okay. Now the remainder of this example is just to flesh out the different branches for the constructs that we want to support. Okay. And the first few are, of course, the part of the expression evaluation. Okay, so a constant evaluates basically to itself. Now you see something a little weird here because we're not returning value. And in fact, if we look at the type, the result type of apply, which is basically the behavior of the execute object, which is the implementation of the interpreter, the result type is not int. The result type is an L value containing an int. And you might wonder, what's going on here? Well, the idea is when we look at the way we're evaluating assignment, okay, that's the answer. So to make it as easy as possible to implement assignment, we always in our interpreter, we always return an L value, basically a storage cell, named or not. In fact, in most cases, not named. Just a new storage cell instance, which contains our result value. In that way, we can evaluate R values and L values uniformly. So to evaluate the right side of an assignment, we just say, okay, apply this evaluator or the interpreter in the context of the current store to the right side. And to evaluate the left side, we'll do the same to the left side. And now the beauty is both of these are storage cells. And we can still use them to complete the actual behavior for the assignment. And we can say, well, let's look inside the storage cell for the right side of the assignment. So that actually gives us the value, meaning by evaluating only up to the point of an L value, we're not losing anything. If we need the R value for it, we can just look inside of it by using get. And that also justifies this decision to say, well, every L value is also an R value because we can always look inside the L value to get the value. Okay? So we can get that R value for the right-hand side and then stick it into the L value we got for the left-hand side. So that's the implementation of the behavior of assignment. Okay? And in fact, in a way, we're doing this to make it more future-proof, because when we introduce objects, so this is a little bit of a sneak preview, when we introduce objects, then variables are no longer going to be the only L values around. Fields or instance variables of objects, mutable instance variables of objects, are also L values. But they can also be R values. So just like we can have x becomes x plus 1, we might have, if O is an object, we might have something that says O dot x becomes O dot x plus 1. So where that instance variable x in object O can play the role of an R value and an L value. And that's why we want to have this generality. You will appreciate it once you're working on that stage of the project. But we want to make sure that once we get to that point where we need this additional generality, we can have rules other than the rule for evaluating a variable, where we can evaluate to an L value. Okay, so again, it's mostly for future-proofing this, for introducing other constructs that evaluate to an L value to which you can assign a value. So primarily the instance variables of objects. But other than that, we don't quite need this here, but it works fine. Although there is a small price to pay, which we'll see shortly. Okay. The price to pay is that now everything has to evaluate to an L value, meaning to a storage location. So that's why here in constant and the other things that should normally evaluate straight to an int value, we have to put those results into a new storage cell. So that's the price. Okay. So that's why all of these result values are wrapped in a storage cell, so that they're all compatible with the idea of returning a variable as a storage cell. Well, how do we return the variable as a storage cell? Well, we just look up the corresponding cell in our global store by performing basically a lookup in this map, and that returns the corresponding value. Some of you might now say, ooh, what if there isn't an entry for this value in the map? We'll address this shortly. That could be a problem. But we'll decide to handle it in a certain way in this example. But in your project, you're going to handle it in a better way. So we'll come back to this shortly. Okay, so let's look at sequence. And you might start rolling your eyes here. There's a fold left, but well, you might have gotten to like folds as a result of the earlier work this semester. But really, all this does is, it goes through the statements left to right, one by one. Again, statements is a 0 or more, right? That's a var arg here in this sequence node. And it just says, okay, it is supposed to return an L value. And let's see. And for some reason, it needed this type annotation. It can probably be improved just by putting a colon here. That's probably better, although it doesn't make a difference. So anyway, what do we get if we have 0 statements? Then it's like a no-op, so we can say, okay, whatever result it is, it's like a nothing. And a reasonable way of representing that is by this null cell. Okay, what if we have statements? Then, well, for each statement S that we get as we go through this sequence from left to right, we will execute it just by saying, okay, let's apply our execution behavior, our interpreter, to the statement in the context of the current store. Now, you don't explicitly see this m prime, m double prime here, because that's just a formal way to express that m has changed over time. Our m is just whatever we pass here as the argument, as the store of the type store, uppercase store. This map from variable names to location cells. Okay, so the primes are implicit here as time goes by and the store changes in place. So you could think about those primes just as snapshots at certain points on the timeline of whatever was currently in that store. So that is not in conflict with the idea that it's just a single object that has a kind of an ongoing life and that we modify in place as we execute the statements in the context of this store object. Okay, so all this does is sequentially execute the statements in the sequence. And what is the result value? Well, it's kind of like in Scala or other more expression-oriented languages. The result value is whatever the value of the last statement happens to be, right? So that's basically what gets returned. And how do you see that? Well, because C, which is the result of the execution of the previous statement, it doesn't appear here. So it means it gets thrown away. So this is a very accurate representation of our understanding of a sequence of statements. If you execute S1, then S2, then S3, for example, you don't care what the results of S1 or S2 were. You only care at that point what side effect S1 and S2 had in that sequence on the store. And then whatever S3 produces, that is the thing you care about, and that gets returned as the result value of the statement. Okay, so this is a little more flexible in that sense, a little more expression-oriented than sequences of statements in the C language, for example. Okay, well, in C there is a construct um, where where you use a comma to separate several statements. So it's kind of like that. Well, several expressions really in C in that case. So in C there is a syntactic distinction between statements and expressions, and we got rid of that for simplicity. But as I mentioned, so we could bring it back, or your parser would probably make sure that the syntax trees are constructed consistently with the syntax, with a concrete syntax where there is a distinction. Okay, now while loops, and what we're doing here is again implementing the formalized definition of the behavior of a while loop, of the semantics. And what it said was, okay, we're supposed to evaluate the loop guard. So let's do that in the context of the current store. And then we'll say, well, if that isn't 0, then we repeat the process. But let's say if it is 0, then we don't do anything. So that would be like, again, returning a null. And that's also consistent with Scala. So loops never return a proper result in Scala. I mean, imperative loops. For comprehensions do, but that's a different story. Those are really combinations of maps and filters and flat maps. So they are actually value oriented. But an imperative while loop in Scala doesn't return a result. Okay, so why is there an actual while loop in there? Well, when the formal semantics called for some, it was kind of a recursive description. Well, what it really was, and now you can kind of rely on the discussions we had on implementations of recursive functions and performance considerations. So ask yourself: is it tail recursive? Is the definition tail recursive? So let's take a look. Where do we want to look? Well, really the last thing is to say, evaluate the loop body in the context of M prime. In the context of M, okay? So basically, if that happens to be a while loop, then we will fall back to that. And it's basically tail recursive. And we're exploiting that in the implementation. So let's take a quick look, just verify everything I just claimed. Let's see. Yeah, no, the tail recursive part is basically this one here, where we're saying we're evaluating the while loop again at the end. And so it gets expressed in the form of this while loop. So the recursive version would read something like, if g_value.get is non-zero, then apply store body, and then recursively apply store s, which is the entire while loop. So it is tail recursive in that respect. It is properly tail recursive. Now, we could have left it as a recursive implementation, but the problem is, well, maybe it would work because there isn't any other recursion in here that's not tail recursive. Everything else is non-recursive. So it would probably work, assuming that the checker for the tail recursion will actually be able to deal with this branching properly. So I think it could work, and I probably wrote it in this way before tail recursion elimination was supported through this annotation, right? But anyway, what I actually like about the way of um, using a Scala while loop is that you can see how we're using a similar construct, in this case the Scala while loop, in our host or implementation language to um, support the corresponding construct in our target language, which is the language for which we're implementing the interpreter, which is our mini JavaScript. Okay, so in a way, this is even though it started out as kind of an optimization of rules 2 and 3 here, in a way, it's more natural even than those formal rules. It maps more directly even to the fact that it really isn't a recursive call, but we're looping in place. So in that sense, I like it better. And I think it's maybe more intuitive. Okay, excellent. So just to recap, we have the interpreter with branches for every construct in our abstract syntax tree, and everything evaluates to a value stored in a cell. Even though for some constructs this doesn't make any sense, such as the while loop, and whenever it doesn't make sense, that's when you play the void card. Whenever in familiar languages the thing has type void, it really wouldn't matter what value you return, but then you could just say, well, I'm going to pull a value out of my hat. And the cell.null predefined one is as good as any other. So that's basically what happens. So the while loop will always return a null value representing this idea of a void value. In the case of sequence, well, if the last sequence happens to be an expression, we can return that expression, and we're basically doing that, or we're producing that expression, and that's going to be nice when we want to generalize in ways such as having a sequence as the right side of an assignment, for example. Then whatever the last expression of that sequence happens to be, that's going to be stored in the left side of the assignment. So it's okay to do that. It's conceivable. Okay, and then in the case of assignment, right, we evaluate both sides down to the L value, the corresponding L value, and then we're just saying, okay, well, we'll reach into the L value to get the R value stored in that location on the right side, and then we're going to stick that into the left side, and then all the other stuff, the non-imperative constructs here, constant through div, right? So these guys, they're just like before, except we're wrapping, actually only up to here, we're wrapping the result value in a cell so that it's compatible with the way we're handling assignment and variables. All right, so now back to possible issues here. Well, back to this place that I pointed out where some of you might be concerned. So what if the variable doesn't exist? Ooh. Then yes, we have a problem. How does this problem get handled? Well, it doesn't get handled. The question is, well, is it okay not to handle it? The answer is, well, it depends, because here what we're doing, you can take the following point of view. So here, just like we're we're using the Scala while loop to implement the mini JavaScript while loop. You could say, well, if there's an error during the interpretation, well, then it's just going to be a Scala exception, right? Because this, the apply method to look up a value in a map, given the key. So this is using the apply method implicitly, using the map like a function. That produces a value of the value type, meaning that if it fails, you're going to get an exception, a Scala exception. And if you're not handling this exception, well, then the exception will ultimately propagate its way up to your main method, and your program will crash, right? And let's take a look at that just to clarify. So here we have a successful run of the little example given. Let's go to that, given in the main method. Well, it looks like we have a little connectivity problem. It's just a little latency problem. Okay, here it comes. Well, okay, let's look at it here. So source main, Scala, what do we have? Imperative. The main method. Excellent. Okay, so I added these comments, as I mentioned in class that I was hoping to do. So, okay, we're initializing our global main memory to these values. Okay, so that's why we're basically creating the map with these initialized storage cells. And then here's the program we're interpreting, and then the concrete syntax, it's a comma here to make it consistent with the parser for this program. The parser you're implementing is better because it's more uses a more familiar syntax with statements terminated by semicolon. Here we have statements separated by comma. So separated means there is no comma after the last one before the closing brace. Okay, so it's a little unfamiliar, but it was easy at the time to rig it up like this. Anyway, so in this main program, we're printing what's initially in the store. So x is 2, y is 3, and r is 0. Then we're running the program s, which is the abstract syntax tree corresponding to this little example here, which, as we discussed, calculates r as an arithmetic expression in terms of x and y. We can express that easily. And so we'll run the interpreter, and then we'll print out the store after running the program. So meaning we're looking at the side effect. And what has changed? Well, y has been decremented down to 0, and r has been incremented by successively adding x to give us 6, as discussed. All right, so that's cool. It works, so no errors here. But what if we made a little change to this and we used some variable here that doesn't exist? So, well, we don't need to change it in the comment. That will have no effect. Let's change it here in the actual abstract syntax tree. So if we try to use a variable z as the loop condition, what happens? And what you expect to happen is, in here, so this is still not working. It's all right. As you expect in here, it would try to look up z, because it would match this case as you drill into it, or as the interpreter drills into it, and then it tries to look up z in the store, but we never put a z in the store initially, so this would fail. And let's actually observe that, okay, we'll rerun the main method in this way. And we get a Scala exception just because in our interpreter implementation we decided to basically fall back to a Scala exception. Okay. All right, so is this a problem? Well, it's a design decision. I mean, for these kinds of initial explorations, that's fine. The question is, can we do better? The answer is yes, and you will do better. So unfortunately, we have a little connectivity issue. But if you look at project 3B, well, okay, we're connected again, so that's good. If we expand this, here it says domain of semantic values and failures. So instead of having the results of expressions represented as just plain values, okay, we're going to have a try wrapper around these. So in this way, we can handle failure much more elegantly, and you can. That's part of the project, to figure this out. So, as you know, there's a way to get a proper exception-free lookup in a map using get. So instead you say store.get. What does that return? Well, an option. And then you could easily convert that option to a try. So that's a good way of doing it. Why do you want a try to represent results that can fail as opposed to an option? Well, because try allows you to annotate the failure. In option, you cannot annotate the none. It's just none. It means it failed. But in try, you can do that properly. So an example of this is in the F algebraic version of the simple imperative executor. So basically, the same idea as this example, but expressed as an F algebra. Now, the F algebra part is, you're not required at all to do this in the project, and it's there just for reference, but you would get extra credit if you did this in the project. Okay, so it's your decision. The example is here, but the thing that I do want to see here is, what I want to show is the idea that the result would be either a value or failure. Okay, so try would be either success or failure, and if it succeeds, you get actually the success, a success instance wrapped around a value of type, of the same type as this trait. And here we have only one possible kind of value, which is int value. And again, the reason that this is a trait is to make it more future-proof so that we could have other kinds of values later, right? I mean, it's a little bit of upfront design, but I wouldn't call it big upfront design. This is more like tiny upfront design, knowing that, well, you might need that flexibility. So, if you know ahead of time that you're going to need it, then why not design it in from the beginning? So that's that part. And now, if we look at the case for a variable, okay, so that's the piece I wanted to show. Okay? Everything else is like the other one, pretty much. Well, there's your your conditional, So you could basically look at that as a guide for your implementation of conditional and block. And if you're not doing it in the F algebraic way, you could F algebraize it. But other than that, just look at the failure handling part. here. So variable lookup, that's the relevant part. So we say here, okay, look up the variable of name of the given name in the store. So let's look at that method. And that's the part I was describing just earlier where we say, well, okay, this gives us an option, looking up name variable of the value for the key name in the store map. This gives us an option, and we can use this fold method, which is basically like a case distinction, without having to write it out as a match case, right? So if it fails, we'll get basically a failure value wrapped in this no such field exception. So instead of the exception, it's the here it's a no such element exception, but instead of the exception, making it all the way to the top level of the Scala, the Java VM running this Scala program, it's wrapped and contained safely inside this failure value. So instead of it controlling you, you control it. So you can look into the failure value and say, oh, there's an exception in there, but it doesn't get ugly like here. Okay, so that's the way in which we're considerably improving on this. So we're not crashing our interpreter when the program that we're interpreting is erroneous, right? That's the idea. The tools shouldn't crash. What your target program could crash, but for example, when you're executing, when you're interpreting something, it shouldn't crash the interpreter. Like in a REPL, if let's say if you're launching the Scala REPL like this, and you're trying to evaluate a variable that doesn't exist, it gives you a civilized error message, as opposed to crashing out of the REPL with no such whatever exception. Okay, so that's basically what we're trying to do, or trying to emulate. All right, so this is how I recommend doing it, like having, oh yeah, it's one more level of indirection here. See, so because we return everything as a cell, and the cell has these values, right? Where before we had just ints. So our original cells are, well, or a parameterized value here. But we want to have multiple kinds of values that we can store in a cell, right? So that's why it's done as an algebraic data type, as opposed to a generic type argument. Okay, so that's that. So our results are always cells, and there could be failure, so that's why we're wrapping a try around a cell. Okay, so that kind of wraps it up, and we're basically done. And of course, so I think you have the different pieces now to complete the interpreter for the mini JavaScript without JavaScript objects. And then the final stage will be to put in the objects, and in this way things are a little bit future-proof. But even if you did things in kind of a more basic way, like here in the simple non-F algebraic interpreter, you could always refactor a little bit to support multiple types of values. So it shouldn't be a problem either way. Okay, great. So this is pretty much it, and we'll be in touch soon. All right.